Welcome to this lecture on orthogonal polynomials. Today we are going to tackle a very common problem in statistics called multicollinearity. Imagine trying to pack a suitcase with three identical heavy winter coats. You waste a lot of space because they all serve the exact same purpose. In regression, using raw polynomial terms does exactly this to our mathematical models. We will learn how to swap those identical coats for a highly efficient, independent wardrobe. Now that we understand the premise, let us look at why raw polynomials cause trouble. In standard polynomial regression, we often model curved relationships using raw powers of our input variable, such as x, x squared, and x cubed. The issue is that as the value of x gets bigger, the value of x squared also gets bigger. They race off in the same direction, meaning they carry highly overlapping information. This overlap confuses our mathematical models, creating a problem called multicollinearity. Because the predictor variables are too closely related, the math struggles to figure out which specific term is actually driving the changes in the output variable. To fix this multicollinearity problem, we introduce orthogonal polynomials. Think of this as reshaping our variables so that each one brings completely new, independent information to the table. In mathematics, two variables are considered orthogonal if they are completely uncorrelated. If you multiply their values together at every single data point and add those products up, the final sum is exactly zero. By transforming our raw values into orthogonal polynomials, we ensure that adding a higher degree term, like a cubic curve, does not change the estimated coefficients of the lower degree terms we already calculated. This makes our regression models much more stable. Let us see how this looks mathematically. We start by defining the general structure of our new regression model. Instead of using raw powers of x, we replace them with our newly constructed orthogonal polynomials, denoted by p0, p1, and p2. In this formula, y is our response variable and epsilon represents the random error. The symbols alpha 0, alpha 1, and alpha 2 are our new regression coefficients. Because the polynomial terms are orthogonal, each alpha coefficient tells us the pure independent effect of that specific polynomial degree. If we increase the degree of our model later, these existing alpha values will not change at all. Now that we have our general model, let us build these polynomials step by step. We start with the very first term, the zero-degree polynomial p0 of x. This simply equals 1. It represents the constant term or the baseline average of our model. It has no x in it, so it never changes. Next, we construct the first degree or linear polynomial p1 of x. We take our raw input data, x, and subtract the average mean of all our x values, called x bar. By subtracting the mean from every data point, we center our data exactly around 0. This ensures our linear term is completely independent of our constant baseline term. Building on our linear term, we now construct the second degree, or quadratic polynomial. To make this term, we take our centered values and square them. However, a squared number is always positive, which means it would overlap with our constant baseline. To fix this, we must subtract the average of all those squared values. In the formula, the fraction on the right represents this average, where n is the total number of data points. By subtracting this average, we shift the parabola down so it is perfectly balanced around 0. If the variance of our data increases, this subtraction ensures the quadratic curve remains perfectly orthogonal to the constant term. Finally, we can state the mathematical rule that proves these terms are orthogonal. This formula is the ultimate test of orthogonality. It states that for any two different polynomials, whether index j is not equal to the index k, the sum of their products across all n data points must equal exactly 0. You multiply the value of the first polynomial by the value of the second polynomial at every single data point, and then add all those products together. If this final sum is 0, the condition is met, and the variables share absolutely no overlapping information. Before we move on, let us see this with a concrete example. Suppose we have a simple experiment with 3 equally spaced input values, x equals 1, 2, and 3. We want to construct the linear and quadratic orthogonal polynomials and prove they are independent. Our first step is to calculate the mean of our x values. Adding 1, 2, and 3 gives 6, divided by 3 data points gives a mean of 2. Next, we find our linear polynomial by subtracting this mean from each x value. For our inputs 1, 2, and 3, subtracting 2 gives us the p1 values of -1, 0, and +1. Continuing with our example, we now set up the quadratic polynomial. We take our p1 values and square them, giving us 1, 0, and 1. We add these together to get 2 and divide by our 3 data points to find the average of the squares, which is 2/3. We subtract this average from the squared terms to balance the parabola. Applying this formula to our data points, we take the squared values of 1, 0, and 1 and subtract 2/3 from each. This gives us our p2 values, +1/3, -2/3, and +1/3. We now have both sets of polynomial values ready to test. Now we perform the ultimate test for orthogonality. We multiply the p1 value by the p2 value for each of our 3 data points, and then we add those 3 products together. For the first point, -1 times 1/3 is -1/3. The middle point becomes 0. The third point is +1 times 1/3, which is +1/3. When we sum these up, the -1/3 and the +1/3 cancel each other out perfectly, leaving a sum of exactly 0. This proves mathematically that our linear and quadratic terms are now completely independent and share no overlapping information. So, we have proven that orthogonality holds by hand. This brings us to a practical shortcut. In the real world, calculating these polynomials by hand for large data sets is exhausting and highly prone to arithmetic errors. Fortunately, statisticians have already done the heavy lifting for the most common experimental scenario, when your input values are equally spaced. For equally spaced predictor values, we use standard published orthogonal polynomial coefficient tables, such as the famous Fisher and Yates tables. These tables provide pre-calculated simple integer values for linear, quadratic, and higher order trends, based solely on your sample size. Instead of doing complex algebra with fractions, you simply look up the whole numbers in the table. Let us see how much faster this is with an example. Imagine an agricultural scientist is testing a new fertilizer at 5 equally spaced amounts, 10, 20, 30, 40, and 50 kilograms per hectare. They want to fit a quadratic curve. Instead of doing messy fraction math, they use the standard tables. We have exactly 5 data points, so our sample size n is 5. We open the tables and look at the linear column for n equals 5, which gives us the whole numbers -2, -1, 0, 1, and 2. Under the quadratic column, the table provides 2, -1, -2, -1, and 2. Continuing with our table values, let us quickly verify that they are truly orthogonal. We multiply the linear table value by the quadratic table value for each of the 5 positions and set up the addition. -2 times 2 is -4. -1 times -1 is +1. 0 times -2 is 0. 1 times -1 is -1, and 2 times 2 is +4. Adding -4, +1, 0, -1, and +4 gives a sum of exactly 0. By simply looking up these whole numbers in a book, the scientist instantly obtained perfectly orthogonal variables, completely avoiding the nightmare of multicollinearity. Now that we have calculated these values, let us visualize what we just achieved. On the screen, you see a side-by-side comparison. On the left, we have the raw polynomials. Notice how the linear line and the quadratic curve both start at 0 and race off in the exact same direction. They are highly correlated, tangling their effects together. Now look at the right side, showing our orthogonal polynomials. The linear trend passes straight through the center, while the quadratic curve forms a perfect symmetrical U-shape balanced around that exact same center point. Because they are centered and balanced, their shapes do not interfere with one another. This visual independence is exactly what makes our regression model stable. This visual independence translates directly into massive practical benefits. Orthogonal polynomials are an absolute lifesaver in experimental design, agriculture, and manufacturing, where treatments are applied at equally spaced intervals. If you use raw polynomials, deciding to add a cubic term to a quadratic model forces you to recalculate all the previous coefficients from scratch because the variables are tangled together. With orthogonal polynomials, the variables are completely independent. This means if you decide to add a cubic term later, the linear and quadratic coefficients stay exactly the same. It allows scientists to test whether higher order curves are necessary without destroying the simpler models they have already built. Let us wrap up what we have learned today. First, we saw that using raw polynomial terms causes multicollinearity because the variables carry highly overlapping information. Second, we learned that orthogonal polynomials solve this by transforming those terms into completely independent variables, where the sum of their products is always exactly zero. Finally, we discovered that for equally spaced data, standard tables like Fisher and Yates provide simple integer values, saving us from complex manual calculations. By using these techniques, you can build complex curved models one independent piece at a time, ensuring your regression models remain stable and reliable. You now have a solid understanding of orthogonal polynomials.